Alright, welcome to Academic Daddy's class. Today we're going to be treating inclined plane. And the inclined plane, when an object is when an object is on an inclined plane, this falls under, or this uses the principle of Newton's laws of dynamics. So it first uses the principle, it obeys the principle of Newton's laws of motion, of linear motion. So when I have an object on an inclined plane, let's say I have an object here on an inclined plane. Let's say this is the inclined plane. So most of the time you see textbooks doing this in such a way that you have triangle around this. You see it this way, but notice that the focus is here. So when you have an inclined plane, there is this law of Newton which says that, second law of Newton. So that law is trying to tell you that whenever you have any, or should I say using the principles of Newton, not just the second law, it's trying to tell you that anytime you have an object, that you should first check the forces acting on that object, then before you consider the motion. So if I'm looking at this triangle that they normally form, this is more like the vertical axis of the earth. Vertical axis of the earth. Then this is the ground, which is horizontal. So I will now use this to analyze it. So when I want to analyze this motion on an inclined plane, I will use this concept, because this is the earth. Whatever movement this is doing is on the earth. But when I want to get the dynamics, so for inclined plane, always get first the dynamics of the inclined plane. So before you move to getting, before you move to the kinematics of an inclined plane. So with dynamics, we are checking the forces acting on these objects. That's what dynamics is all about. When you're treating motion, I'm paying attention to the forces, or you say the forces that cause the motion. That's what dynamics is all about. So I will check the forces acting on this object before I will now come and look at the kinematics aspect. And notice that this object is first this way. Now notice that if I have it to be inclined on this, now let's say I have this to be inclined. So when I'm considering the dynamics is what I want to consider now. The dynamics. So this object is going to be in such a way that it has weights acting on it. First of all, look at it this way. Let's say the weight of this object now, as is on this plane, it is exerting weights on this object. Let's say this is the weight. There's the box itself, the weights. The impact on the object is being felt downwards. And we know that if that is the case, we know that weight as a field in physics is discussed with mg. So let's say this is the forces acting this way, the weight of this object. So we can see that this axis here, let's say first of all, if this object is horizontally, this axis is the y-axis, and this axis is the x-axis. Shebi? So which means that if I happen to turn the object this way, this axis is the y-axis, this axis is the x-axis, x, y. So if I know it, let me use that same concept. Notice that everything acting this way the y-axis. So we normally say that there is what we call normal force, and this normal force acts at 90 degrees. So notice that this normal force, if I have this object this way, normal force will be acting this way, while gravity will be acting this way. So I need to use that same concept. If I turn this now, I'll see that the normal force should be somewhere here. If I turn this, it will now mean that this thing, the normal force will be here at the center. So that is the normal force. So let's say that I bring it down. Why gravity itself? If I turn this object the way I've turned it now, gravity is not acting on this object like this. No, gravity does. Notice that this gravity is the force that tends to pull an object to the center of the earth. So gravity can never turn. Gravity can never turn and act this way. Gravity will always be this way, vertically, straight down. So let's come and apply it here. Gravity on this will be in this format. Let's use this object. So gravity on this plane, everything here, starting from this point, will be acting straight down. I see it. Gravity acts this way. So let's say I call this now mg for gravity, force of gravity. So notice that this normal force is acting upwards, n. Now notice that if it's acting upwards n this way, I told you that everything about this, that is this weight, this block itself, this block, as it's acting, as it's on this plane. Remember that what we are doing is the dynamics of the inclined plane. As it's on this plane, you can see that everything this side is y-axis. So let's go back, trace it now. See that the normal force is going up. Notice that if we trace this line, that the normal force extended upwards, you see that it runs down. But what we are using this to compare when we are down here is simply the weight. Remember we said that the whole weight of this is this side. So that means that this side will be the y-axis. And if that is the case, y-axis in terms of, we are checking this. So but I brought the y so that you will see the middle. Don't worry. Then this particular line here, notice that I use this to do it, but if I bring it down, you see that everything this way is x-axis. So let's do it in such a way that we already have a center where everything is happening. The y-axis running down, that is normal reaction up. There will be equal balance on it, and everything on this side is going to be countered this way. Let's say this is x-axis. So this is the weight on x-axis. This is the weight on y-axis. So what this thing means is simple. This is weight on y-axis. What it means is simple, is that whenever you have an inclined plane this way and you have an object, simply take it that that object, as you're seeing it from the center, it has weight acting on it, and this weight, notice that y-axis on this side is also this side. Then the x-axis, this is the x-axis because you can see this horizontal. This is y because of this side. So this part now gives you the normal reaction. Then this part is straight down, and this part that is straight down is straight. If you have something this way, you can never come and say that gravity is this way. No, gravity is this way. So the gravity on this is this way. So let's say that it cuts through this now and comes down here. So you can see that what you've created here is a right angle triangle. So the dynamics, what this means is that the dynamics of an object on an inclined plane can be gotten using this. And notice that when I have a triangle like this thing like this, the angle is going to be here. If you draw it where you see what I mean. If I have something of this nature, the angle is always here, theta. So I need to know that. So this is the angle theta. So That means that, remember that this is mg, so which means that on the x-axis I have wx. Now notice that if I have wx here, this can also be wx. That means that, remember that what gave me this line was gotten by gravity, which means that my mg is here. So that is the principle I want you to get. So if I know this, we can now employ SOHCAHTOA. So we can simply, even without stressing myself, anytime I see an inclined plane, the principle is to first get the dynamics of the inclined plane. So even not just inclined plane, anything about motion that the dynamics of the objects on the inclined, anything about motion that has to do with force, first get the forces before looking at the, then get the kinematics. So all those things, all the kinematics of the objects. By kinematics of the object, I mean get the motion of the object. So everything I've done here that you see me doing here, I said this side is x because the box, this is the rectangle, this is the x side, this is the y side. So that is what I used. So everything I've done here can simply be put in analyzing the dynamics. Is simply, if I come here and do this, get the center, gravity should be acting this way. So get gravity. The weight, there is total weight acting on this downwards this way. So simply get it from, if you draw box, extend the box. So when you extend the box, get the straight line. I seen it. Get the straight line that is for y-axis. That is the weight on the y-axis, because this thing is exerting weight downwards. That is, the weight is exerting on this is downwards. That is this way. Then the force of gravity acting on it is this way. So you can see that even this met here, this line applying vectors, this thing that I have here, this gravity that is acting here should be acting here as well. It's acting on this side. It should be acting here. This place and this place is equal. This line and this line is equal. So once I get this triangle, I will note that this is the angle, because if I have a triangle, this side, the angle is standing, the triangle is standing. If I have such a triangle, if you bring it down, it's descending with this. This is the hypotenuse. This is the hypotenuse, which means that this side is the theta. So that's just the same thing that we did. So if we know this is the object, so we'll now use this to solve. So applying SOHCAHTOA now, I will now have that. Remember that this is an inclined plane. So applying SOHCAHTOA, I will now have SOHCAHTOA. So sine theta will be equals to opposite over hypotenuse. Now remember, if I look at this very well, which side is theta? This is theta. The side facing theta is opposite. So this is going to be sine theta is equals to wx all over. Remember that this line gave me gravity and it's mg. I can make anything subject of the formula, but mg is force of gravity, so this is the one I'm looking for. So which is weight on x-axis. So weight on x-axis is equals to mg sine theta. Now for cos theta is equals to, that is adjacent over hypotenuse. So right here, the longest line is hypotenuse. The side facing the angle is opposite. That means the remaining part is adjacent. So wy all over hypotenuse is mg. If you like, call it magnesium. Cross. This is going to be wy is equals to mg cos theta. So you can see that. So remember that the force that acts on an object at perpendicular, that is any object, if I have this going this way, any force that acts on this way, this is the 90 degrees of this thing, of this object down here. The force that acts on this now, this way, is the normal force. If I have it this way, the force that acts on this is upward, is down, the normal force or normal reaction. If I have this way, force that acts on this way is normal reaction. But if I have this way, the force that always acts on every object this way, it will always be this way, vertically, is force of gravity. And we say that this force of gravity is the force that tends to direct the motion of a body downwards. So if I know that that's force of gravity, so to always try to bring it vertically down, it's not playing with you. So that is how we get this. So Wy is mg cos theta. So which means that we can now come and check. As I have this thing now here, let's check what are the forces acting on y-axis. Since we know that everything this side is y-axis, remember, if we have an object like this side is the y, this side is the x. If you turn it to be at an angle, you can see that this is the y. So what are the forces acting on the y-axis? So we can see that the forces, everything acting on the y-axis from everything we've done here now, is simply this wy, weight on y-axis, and this normal reaction. This one is going upwards, then this one is acting here downwards, that is here on the y-axis. We can't really call it downwards, but you just need to know that everything, as you have this object, the only force acting upwards that you can see is any normal reaction, and the one acting downwards on the vertical axis is the wy. That is why we call it weight, tending to drag it down, weight. So you can see that whatever this one has, this one is having it. So there is no force act. In fact, the way to visualize it is that this thing cannot come and fly up. It will only move downwards like this. So there is no force in the vertical axis. So we say that N is equals to W and is equals to 0, because there is no force there. Or you can say, if you don't want to do it like this, remember that this is upwards, this is downwards. And I taught you in class that in forces, anytime you see something moving, action minus reaction, that is action forward minus reaction. In this case, normal reaction is the action. This one is the downward, the backward, the down. So W equals to 0. Even if you do W minus N, it is still equals to 0. And they are still going to give you the same, because once this one crosses over, it becomes N, it becomes W equals to N. So whichever way you do it is the same. And the W here is at y-axis. Y-axis, y-axis, y-axis. And remember that Wy, we've gotten it to be something. So which means that N is equals to mg cos theta. In most cases, you will see us making use of this. So N is equals to mg cos theta. You need to note it. That is the first equation under what we are doing here for vertical axis. So for vertical axis, no force. Oh yeah, let's come back. Looking at this now, as you place this thing here, this is the incline. The minute you leave this thing, as you place it here, remember we are not considering static, we are saying it's inclined, nothing is holding it. The minute you keep it here, it will start sliding down. And as it's sliding down, it's going in this direction. Is it not true? So if it's going in this direction, you can very well see that this is just one object. And employing the first and second rule of Newton, the first and second rule talks about just an object. When you have just an object, the forces on that object is simply F equals to ME. But when you have two, let's say you have two objects here, the first one will be F equals to MA, the second one will be there's force moving this thing upwards, and there's a force acting on it backwards. Why is it backward? Because this particular one, the weight will tend to be dragging this one back. So we'll simply do this force. There's a force that will be here trying to put this one forward. If there is, it will be given. So remember, we're considering force. So the force that this one possesses that it can move here is F, minus the force on this one, which is this one from here, by virtue of this. So minus F2 equals to MA. So but notice that what we are treating here is just one object. So the force acting on this way is mg. The force acting on it is mg. Remember, everything here, as this thing is going this way, is weight, and weight is given by mg. That is what we are treating here. So the force acting on this is mg, and if this is the force acting on this way, which is mg, it simply goes to say that since it's at horizontal axis, I can say that anything horizontal axis, the force on the x-axis here is equals to force is equals to mg mg equals to x-axis, and you know that everything on the x-axis is wx, should be equals to wx. So I can choose to use any of these. So I can say F equals to mg, depending on the question, equals to mg sine theta. So it depends on what I'm given in that question. So, and remember that force is ma, should be? Force is ma. So I can say force ma, if I don't represent this, is for one object. One object force is ma, is equals to mg in this case when it's coming down, and is equals to forces, or should I say weights, on x-axis. Weights on x-axis. And if that is the case, we can see this. So whenever they ask me find the acceleration of a body on an inclined plane, I can use the same principle to say it does not start inside here. I'm just using it to indicate something. So I can use the same principle now to say that MA, which is force, or you say weight on x-axis, is equals to mg sine theta. And remember that this is equals to the force on x-axis. Yes, this everything here gives me force on x-axis. So, and it's just one. So I can say that MA in this case is equals to mg sine theta. Because if I come and say, since what is happening here is equals to mg, that is the force acting here is mg. Watch. If I come and do, watch, since this is mg, this is it. So, and I know that it is at an angle, and the angle we found it to be sine theta. Are you seeing it? So this is the so for that reason, I can now say MA, force on this x-axis, is going to be the same thing as saying cancel this, cancel this. So acceleration of an object on an inclined plane is simply g sine theta, since it's on the x-axis. So we get it from the x-axis because there's movement on this x-axis. When this thing starts sliding, the acceleration there as it's moving, we can calculate it by doing this. We know that of gravity, the one of gravity, which is this one that we got, is always 9.8. But anytime we talk about horizontal movements, as something is moving horizontal, we talk about acceleration. Then we talk about something is moving vertical, we talk about g. So you need to know this principle. So with that said, we've gotten how to calculate acceleration that is acting on the on an inclined plane. So how many now? So we've gotten so, but the summary of everything we did here is simple. We use this to find the dynamics, and you see all these things we are doing here, guys, over here, all these things we did here. Like, notice that we are talking about acceleration. Is it not true? Notice we are talking about acceleration, and acceleration has to do with motion. So this falls under kinematics of inclined plane, of an inclined plane. This was under kinematics of an inclined plane. So under this, for the movements here, there is no movement, but you just need to know that N is equals to W, because there is no movement on the vertical axis, but here there is movement. So x-axis, from x-axis movements, so this one. So if you can clearly see now, you see that when we are treating kinematics of an inclined plane, that's where when we consider this, because you can very well see that there is movement now down this plane. There's movement down this plane, and there can be movements down here too. So, and this is weight on y-axis, that is force here, normal reaction, is equals to the force acting on it on the y-axis, which is this way. So we got it to be equals to mg cos theta. How I normally know this is simple. Whenever I want to get the components, like this thing now, all these things I did here, I can easily say, there's all this thing I got here, x, I'm used to x being cos theta, but whenever it's inclined plane, it becomes sin theta, because things are meant to be this way. But when it's not this way, it means it's abnormal, it's not standing right. So I now put this. If you want to learn it that way, you can still. The same thing, I know y to be sin theta, but whenever it's inclined plane, it's now hanging. Something is hanging, so it's no longer normal, it's unusual. I put this, then times mg, that is the mass and gravity that will be acting on that object. Very simple. Whichever way you want to use and remember it. Now there's something I want to point before I round up this video. Notice that if I have an object on an inclined plane, when it starts moving down, let's say there is friction. Let's say there is friction on this. It can start, there are three cases. It can start moving down. Notice that I like drawing my inclined plane with this and not doing that triangle, because that's what confuses most students. So I can have, whichever way you want to draw it. If I have an inclined plane this way, I can have this way. You see that I can have when this object is being pulled up, something is pushing it up. Then I can have another case where I have this and it is down at the bottom. Notice that the movement is what we are dealing with, so I need to complete it. This is like the vertical axis of the earth. This is the ground level, x, y. Then vertical component of the earth, ground. Vertical component of the earth, ground. So let me draw this one well. So I'll have when it's moving downwards, when it's going up, and when it is like here, it has not started moving. These are the three cases. The three cases: case 1, case 2. Okay, let me call this case 3. This should be the case 1. So for case 1, you need to remember that we normally say that static force or static friction, static frictional force. And we know that friction is the opposing force. I normally tell my students that friction is to the horizontal axis what gravity is to the vertical axis. When you want something to move up, gravity will bring it down. When you want something to move forward, friction wants it to go back. If you want it to go back, friction wants it to go this way. So if you want it to go this way, it means forward, this one. So if I know this, static friction, we say that is directly proportional to normal reaction. I normally say that static friction is equal to introduce proportionality constant, which is mu s times n. So if I have this case, when an object is to come, that is static, when it's not moving, I can simply say that what I have there is static force equals to mu s, then normal reaction. This, I'm saying that this static friction will be equals to normal reaction in the sense that there is no movement. You need force. There's force acting on this to keep it resting. Then there's force naturally acting on any object standing on its own. If somebody is standing now, gravity is acting on it, there's tendency for that thing to move up. So it's always there. Normal reaction, normal force is always there. So is equal. Then notice that this will be Fs